Let's take a look at example 5. Suppose the committee from example 4 will choose 3 members to form a subcommittee. How many ways can the subcommittee be formed? So let's take a look back at example 4. In example 4, we had a committee of 10 members. So we have this committee of 10 members, and we're going to choose 3 members to form a subcommittee. So the first thing that I want to address is, how is question 5 different from question 4? Well, the difference is in question 4 we were selecting 3 members, but those 3 members were to be assigned an office. So there we had a chairperson, a vice chairperson, and a secretary. In example 5 there are no offices. So here we're just selecting 3 people. So what do I mean by that? Well, the difference is that in example 4, the order in which the individuals are selected matters. But in example 5, the order in which the individuals are selected doesn't matter. So think of it this way. Suppose that the 3 members that were selected in example 4 are designated A, B, and C. So if member A is selected to be the chairperson, and member B is selected to be the vice chairperson, and member C is selected to be the secretary, so those would be the 3 members selected, and this order matters. A's the chair, B's the vice chair, and C's the secretary. But if I selected those same 3 individuals, and if A was the chair, C was the vice chair, and B is the secretary, that would be a different outcome. Well, in example 5, these 2 outcomes are the same outcome. If I'm selecting 3 individuals to be on the subcommittee, it doesn't matter who's first, second, or third, like it does in example 4. So the order that the individuals are selected has no meaning in example 5. So these 2 outcomes would be the same outcome in example 5, but they're different outcomes in example 4. That's the distinction. Well, how many different outcomes are possible if I'm selecting members A, B, and C? Well, if I have B first, A second, C third, that's a different outcome in 4, but it's the same outcome in 5. If I have B first, C second, A third, that's a different outcome in example 4, but it's the same outcome in example 5. And likewise, if I have CAB or if I have CBA, these 2 outcomes are different outcomes in example 4, but they're the same outcome in example 5. So these 6 outcomes are different outcomes in example 4 because who's first, who's second, and who's third matters in example 4, but they're the same outcome in example 5 because in example 5 it doesn't really matter who's first, second, or third, it just matters if they're picked or not. In the same way, if I had 3 different members, so suppose I had members D, E, and F. Well, again, D, E, and F would be different from D, F, E in example 4, but in example 5, those 2 outcomes are the same. Likewise, if I have E, D, F and E, F, D, those are different outcomes in example 4, but they're the same outcome in example 5. And if I have F, D, E and F, E, D, those are different outcomes in example 4, but they're the same outcome in example 5. So regardless of which 3 individuals end up with an office, in example 4 there's going to be 6 different outcomes that in example 5 would be the same result. So how do I answer example 5? Well, example 5 is not really a permutation problem because I'm taking 10 objects and I'm selecting 3, but because each 3 has 6 duplicates, I have to divide that result by 6. Why 6? Because regardless of which 3 individuals I end up with, there's going to be 6 duplicates that in example 5 is really the same result. Well, in example 4 we saw that the permutation of 10 objects selecting 3 at a time is 720. And so if I take 720 and divide by 6, that is 120. So there would only be 120 different ways of forming this subcommittee. Now, why 6? Why did we end up with 6 outcomes? Well, if we think about 3 objects, and we think about the different orders of those 3 objects, then that would be 3 times 2 times 1 different outcomes, which gives us the 6. So in other words, that's coming from 3 factorial. We're getting 6 from 3 factorial. Again, if we're selecting 3 individuals, and if they're A, B, and C, how many different ways can A, B, and C be arranged? Well, they can be arranged in 3 times 2 times 1 different ways, or 3 factorial different ways. So what I'm really doing here is I'm dividing the number of permutations of 10 objects selecting 3 at a time, I'm dividing by 3 factorial. So what I really have here is the permutation of 10 objects taken 3 at a time, and we're dividing by 3 factorial, which ends up being 720 divided by 6, which gives us the result of 120. So to answer example 5, the answer is 120. There's 120 different ways that we could form this subcommittee. Now, the problem in example 5 is not a permutation. I already said that. Instead, it is a combination. So I want to define what a combination is, and I've kind of already explained the difference by looking at example 4. The main difference between, again, example 4 and example 5 is that in example 4, the order in which the 3 objects are selected makes a difference. In example 5, the order in which the 3 objects are selected doesn't make a difference. Again, these outcomes here in example 5 are all really the same outcome. It's those same 3 individuals on the subcommittee. Doesn't matter who's first, second, or third. But in example 4, it matters who's first, who's second, who's third. That's the real distinction. So definition, combination. If we choose R objects from a set of N distinct objects, we say that we are forming a combination of N objects taken R at a time. The notation C parenthesis N comma R close parenthesis or subscript N capital C subscript R denotes the number of such combinations. Also, the number of combinations of N selecting R at a time is equal to the number of permutations of N selecting R at a time divided by R factorial. Or in other words, that's N factorial divided by R factorial times N minus R factorial. So this is a formula for determining the number of combinations of N objects selecting R at a time. Now, as I've already tried to indicate, the distinction between a permutation and a combination is whether the order of the objects matters. If the order matters, then we have a permutation. If the order does not matter, then we have a combination. So again, looking back at example 5 before we look at other examples. So in this case, we had 10 members and we were selecting 3 of them to be on a subcommittee. And the order in which those 3 members are selected does not matter. So this was really a combination of 10 choosing 3 at a time. Or we could also denote that as a capital C with a subscripted 10 in front and a subscripted 3 in back. And then by our definition here, that would equal 10 factorial divided by 3 factorial, that's the R factorial, times 10 minus 3 factorial. So in other words, this would equal 10 factorial divided by 3 factorial, 7 factorial, because 10 minus 3 is 7. So if we multiply that out, well, 10 factorial would equal 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'm going to call that 7 factorial. And the reason why I'm doing that is because I have 7 factorial on the bottom, which also means 7 times 6 times 5 times 4 times 3 times 2 times 1. So those are going to cancel. But I also have 3 factorial, which means 3 times 2 times 1. Well, 3 will cancel with the 9, leaving 3. 2 will cancel with the 10 leaving 5. And if we multiply 5 times 3 times 8, well, 5 times 3 is 15, and 15 times 8 is 120. So we get 120. I also want to mention that we have a combination command on our TI calculators. So if we go to Math and Probability, number 3 on my TI calculator is for combinations. And that command works just like the permutation command works that we used previously. So I'm going to start by typing in the 10, then Math and PROB, and then choose the NCR command and type in the 3, and that gives me 120. So on our TI calculators, we can do this directly once we know that we have a combination problem. If you don't have a TI calculator, you have a different brand of calculator, you may also have this capability, you'll have to check your user's manual. If you don't have a graphing calculator at all that can do this, then you'll have to work it out the way that I've demonstrated here. So let's take a look at example 6. Joan plans to rent an apartment for next semester. How many ways can she choose 3 roommates from a group of 7 friends? So Joan is going to choose 3 roommates out of 7 friends. So this is a combination problem. The order of the 3 friends that are selected doesn't really matter. It just matters if they're selected or not. So this is a combination of 7 items choosing 3. Or again, if you prefer, we could write that as 7 choose 3. Now just to point out the reason why I'm showing you 2 different notations for this, the CNR notation here, that is the notation used in our textbook, but this notation is the notation used by our TI calculators. And so we need to be familiar with both of those notations. Both of them are fairly common. So anyway, if I want to work this problem out by hand, this would be 7 factorial divided by 3 factorial times 7 minus 3 factorial. So it's really 7 factorial divided by 3 factorial times 4 factorial. Now 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'm going to just keep calling that 4 factorial. And 3 factorial means 3 times 2 times 1. And then 4 factorial means 4 times 3 times 2 times 1. So I'm just going to leave that 4 factorial. And that's going to cancel with that. And then 3 times 2 is 6, which will cancel with the 6 on top. So I'm left with 7 times 5, which is 35 on top, 1 on the bottom. So that's just 35. So there would be 35 different ways that Joan could select 3 roommates from her 7 friends. Again, this is a combination because the order of the 3 roommates doesn't matter. Now again, I could use my calculator. So I would type in 7, then Math, Probability, Combination, choose 3. And so that gives me a result of 35. So again, Joan could choose her 3 roommates from her 7 friends 35 different ways. Take a look at example 7. In a game of poker, a hand consists of 5 cards that are dealt from a standard 52 card deck. How many different poker hands are possible? Well, we have 52 cards, and those cards are distinct, meaning we can tell them all apart. And we're going to select 5 of those 52 cards. Now in a poker hand, it doesn't really matter which card's first, which is second, which is third, and so on. We're just going to have 5 cards. So this is another combination problem. So this would be a combination of 52 choosing 5 at a time. Or again, using our other notation, combination of 52 choosing 5. Now if we want to work this out by hand, this would be 52 factorial divided by 5 factorial times 52 minus 5 factorial. Again, just to point this out, when I have NCR, our combination of n choosing r at a time, it is n factorial, and then it's r factorial, so it's the first number factorial divided by the second number factorial times the difference of the two numbers factorial. So 52 factorial on top, 5 factorial on bottom, and then 52 minus 5 factorial on the bottom. Now 52 minus 5 is 47, so that is 52 factorial over 5 factorial 47 factorial. Again, 47 because 52 minus 5 is 47. So if I have to work this out by hand, then 52 factorial would be 52 times 51 times 50 times 49 times 48 times 47, 46, 45, all the way down to 1. Again, I'm going to stop there because I'll be able to cancel that with the 47 factorial on the bottom. Now 5 factorial means 5 times 4 times 3 times 2 times 1. And so the 47 factorials will divide out, and I can also divide out these other numbers. So for example, 5 times 2 is 10, and 10 will cancel with 50, leaving 5. 4 times 3 is 12, and 12 will cancel with 48, leaving 4. So again, the 5 times the 2 was 10, and 50 divided by 10 would leave 5. 4 times 3 is 12. 48 divided by 12 would leave 4. So all I really have to do is multiply 52 times 51 times 5 times 49 times 4. So if I do that, 52 times 51 times 5 times 49 times 4, that is equal to 2,598,960. So there are 2,598,960 different poker hands possible out of a standard deck of 52 cards. Now we could have also done this problem just by typing it in directly, which I would recommend if you have a calculator that can do that. So it would be much easier for me to type the 52 math probability, choose combination, and we're selecting 5 at a time. And so that gives me the same result, 2,598,960. So there are 2,598,960 different poker hands possible. Let's end this video by looking at example 8. So example 8. In the card game Spades, a hand consists of 13 cards that are dealt from a standard 52 card deck. How many different hands are possible? So example 8 is a lot like example 7, except in example 8 we're going to be dealt 13 cards instead of 5 cards. So we're going to be looking at a combination of 52 choosing 13. So again, we can use either of our notations. Either way, this is a combination of 52 objects. We're choosing 13 of those objects. Now again, it's a combination because the order in which the 13 cards are dealt doesn't matter. That has no real distinction, and so that makes it a combination instead of a permutation. So this is going to equal, by our formula, 52 factorial divided by 13 factorial times 52 minus 13 factorial. Now 52 minus 13 is 39, so this is 52 factorial over 13 factorial times 39 factorial. Now, this is where the work gets a little more challenging because we have a lot more numbers to write out to be able to multiply out and cancel and so on. So 52 factorial means 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45 times 44 times 43 times 42 times 41 times 40 times 39 factorial. And again, I'm writing 39 factorial because that really goes 38, 37 all the way down to 1, but I'll be able to cancel that with the 39, 38 all the way down to 1 with this 39 factorial on the bottom. Now 13 factorial means 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then again, I have 39 factorial, and that's going to cancel with that. So what I have to worry about is how can I simplify this? Well, let's start. Looking at the bottom, 13 times 4 is 52. So that will cancel with the 52 on the top. So 13 times 4 is 52, cancels with the 52 on the top. 12 will divide into 48 4 times. So 12 will cancel with 48, leaving 4. Now that 4 will cancel with the 8, leaving 2 on the bottom. And then I have 11. 11 will cancel with 44, leaving 4. And this 2 here times this 2 will cancel with that 4. 2 times 2 is 4, and it cancels with that 4. 10 times 5 is 50, so that'll cancel with 50. 7 times 6 is 42. That'll cancel with the 42. So the only thing I have left on the bottom is 9 and 3. Well, 9 will cancel with the 45, leaving 5. And 3 will cancel with 51. 3 will go into 51 17 times. So I finally have everything on the bottom canceled. So all I'm left with on the top is 17 times 49 times 47 times 46 times 5 times 43 times 41 times 40. So if I bring in my calculator to do that work, 17 times 49 times 47 times 46 times 5 times 43 times 41 times 40, that is 6.350135596 E11. Now that E11 is scientific notation. So this is 6.350135596. And again, that's scientific notation, so that's times 10 to the 11th power. Now that means that this decimal point is going to move to the right 11 places. So behind the 3 would be 1 place, behind the 5 would be 2 places, 3, 4, 5, 6, 7, 8, 9. So I get to 9 places behind the 6, and I'm going to have to put a couple of zeros back there for the last 2 places. So that is 63501355596, and again I needed 2 zeros, so again moving the decimal point from where it was here to behind the 0, that's 11 places. So what number is that exactly? Well, that is 635,013,559,600. So there's 635,013,559,600 different hands that are possible in spades. That's a lot of hands. Now again, if your calculator has the capability, it's much easier to just type that in directly into your calculator. So if I do 52 math probability NCR, and we're choosing 13, so that is the same result. Again, that is 635,013,559,600 different spades hands that are possible. So I highly recommend that you use your calculator to do these computations if your calculator has the capability. If not, it's not unbearable to do this, but problems like this become much more challenging. Now we have one more topic to talk about in this section, and so we'll do that in the next video.